Alrighty, 712, common ion effect. As I said here, several highlighters and colored writing tools are extremely helpful. You'll see why. Alright, so the common ion effect is about Le Chat's principle, and it's about reducing solubility because you have a common ion. So as a reminder, solubility is about dissolving something in solution, and so the common ion would be something that is in common with the thing you're trying to dissolve. And again, it'll make more sense with an example. So, a previous example we did is this one, this this equation right here. And so you can see that if I have water on the top and I have this solid, it can go in equilibrium to the ions versus the solid form. As a recap, this is a solid, so if I add more of this reactant, it doesn't affect the K value. But if I add product, it is aqueous, so that will affect the overall what's happening in the system, because this is part of the products in the K value. So if I increase the products, I have to compensate for that to whichever K I have. And so then you're going to reverse the, you're going to increase the reversed rate. Okay. So what if I add something else and it has a common ion to something in the reaction? So in this case, we have iron 2 and hydroxide, and so I'm going to add something that has a common ion to that. So, for example, what if I add iron 2 chloride? And so we need to check the solubility rules. So here you can see the solubility rules for this. And so we're talking about iron 2 chloride. So if I look at the chloride ion here, it says insoluble with these ions and soluble with everything else. So for iron 2 chloride, it's going to be a soluble thing, so we can dissolve it in water. And so here is the two things. So this is the original equation given earlier. And so this is the new thing I'm adding. So again, I'm adding iron 2 chloride as a solid. And so since it can dissolve, it's going to dissolve into these two ions in the solution. And so if we think about adding this common ion, so in this case I have highlighted it in green here, I have added more iron 2 ion in this. And so whatever the saturated solution of this was, if I increased the amount of iron by adding iron 2 chloride, I have now increased the iron 2 ions in the solution. And so because I've increased that concentration, I now have to shift the equilibrium. So it's going to shift to the left. As a reminder, you want to talk about increasing the rate. So really you want to say you're increasing the reverse rate of this process. And so you're going to make more of this iron hydroxide in order to compensate for the fact that you added iron ions. And so you're lowering that solubility at whatever temperature that is, because you have increased the amount of iron 2 ions, and so therefore you have lowered the solubility of the original solid in there. And so not only is adding a common ion going to affect your solubility in order to dissolve stuff, pH will too, and we'll talk about that in Unit 8. Okay, so here's an example. So go ahead and read through it real quick. Okay, and so before we do this example, what does this KSP mean? So I see a KSP value of 1.8 times 10 to the negative 11. And so as a reminder, if your KSP is very small, that means it will not really dissolve that much. And so if I look at this chart, because AgCl is not part of the one you have to memorize, I see chloride ions insoluble with Ag+. And so does that make sense, this KSP value? Yes, it does, because insoluble means it won't really dissolve, but remember that technically you have a tiny bit that can dissolve, and so this is that tiny bit that can. To 10 to the negative 11 is such a minuscule number that it will barely dissolve, and so that's why this makes sense. Okay, cool. So we're going to go ahead and do this example real quick. So how many grams of AgCl could dissolve in a liter of water? And so I did a rice table real quick to show how to do the KSP. As a reminder, the solid part, because it's solid, it's not part of the K value. And so you're not doing this. And so I set this up. I have my zeros and my plus X. Cool, right? And so just like the last section, we're going to set up our KSP. So remember, it's products over reactants. You do not include solids or liquids. So in this case, it's just these ions. And so that's what I have here. And so then I know my KSP value is this. Each box here is X. So I plugged it in to be X squared. And so therefore math, I have my X value is just square rooting that, and so my X is equal to these concentrations, and so therefore I have my molarity. And so did I actually answer the question? I go back to the question. It says how many grams of AgCl could dissolve. So right now I have the molarity of the ions. So that is not the answer to the question. And so remember that big M is moles per liter, and so I can convert this. So I skipped some of my steps in my stoich because I got kind of lazy. But essentially, I have a liter of water, right? And so because Ag plus and Cl minus is 1-to-1 with AgCl, I skipped the conversion step between converting from one ion to the AgCl, but you know, whatever, it's fine. And so then I have my molarity, my liters cancel out, and then this 143.22 grams per mole is the molar mass of AgCl, and then I plug that into my calculator, and this is how much can dissolve. Now notice it's 10 to the negative 4. That's hecka small. That is a tiny, tiny bit that can dissolve, and again, that makes sense. In the solubility rule chart that I showed earlier, it said AgCl would be insoluble and barely any of it dissolves, so it totally makes sense why we call it insoluble. Okay, so let's say I have some solid AgCl in a liter, and it was in a solution of sodium chloride. So how much mass of this AgCl could dissolve? So remember, the solution has NaCl in it. So there is Na plus ions and Cl minus ions. Notice I highlighted Cl minus. So in this particular problem, I am given the initial concentration of Cl minus. Because remember, these are dissolved in solution, so I have that, okay? Versus in part A, I had nothing in it, because right now I'm dissolving this in water. And so part B is instead putting it in a solution of salt already, in this case, sodium chloride salt. And so just to recap, you can put a little solid here, and then you put AQ, right? And so that's just dissolving everybody. And so right now I'm putting my rice table. Now notice I have an initial value for Cl minus because again, I already have some Cl minus, and so I'm starting off with that. I don't have any Ag ions yet because I have yet to add it. We're trying to figure out how much would dissolve because of putting this in here. So that, again, is where I got this value. So then I do my rice table like usual. So I got my two values there. And so KSP is really small from earlier, so I could check if the shortcut works. And so as a reminder, the shortcut is KSP times 100, and is it less than the concentrations of both of these? And so it is. And so I can round my Cl minus E value here to be 0.55. Again, if the shortcut didn't work, then I have to just use 0.55 plus X in my constant for KSP. And so KSP, again, I listed it here because as a reminder, that is 1 point on an FRQ. And then I plug in my KSP value for AgCl, and then I have my 0.55 from here, and then Ag is X. And so I math that, I get my X, and then I could write down my concentrations of each of these. So I have my concentration of Ag plus and my concentration of Cl minus. So here is my stoich math, and I explained where each of these parts come from down here in this purple highlight. So I have a liter of solution. I have the concentration of Ag plus ions from equilibrium, because that's what this is. And then here is the ratio that I skipped in the previous part. So for every 1 mole of Ag plus, I have 1 mole of the compound. So in this compound, there's only one. There's an invisible 1 here, so that's where that 1 comes from here. And so that's that. And then I took the molar mass of this, and so I get how many grams of AgCl would dissolve. Now notice it's 10 to the negative 9. So earlier, if I just go back to the previous slide real quick, here, it's negative 4. And so negative 4 is way bigger than negative 9. It's still a small number, but now, because of the common ion effect, you can see with the math that barely any is dissolved, because 10 to the negative 9 is such a tiny, tiny number. And so Ag plus and Cl minus, again, because there was a common ion from this salt, the chloride in this case, we are dissolving even less silver chloride. Cool. Stoich. Here's the stoich again. I'm just showing it again. And again, this is where the values came from. So make sure you understood where those values came from. Okay, so let's say part B was a different salt instead. And so this is a very important part. That's why I put important. And so what if it was iron 2 chloride instead? So here is my, dissolving of iron 2 chloride, right? And so in solution, be very, very careful. This has 2 moles of chlorine ions for every 1 mole of FeCl2. And so notice Cl minus concentration is 1.1 because we're talking about just chloride ions. So be very, very careful about this when mathing it. Okay, and so this is the original answers from earlier, ignoring this now. And so part A was negative 4, part B was negative 9. And so again, you want to see the common ion. The chloride from the salt is forcing the equilibrium to shift because to make the solid, or you have to make the solid in order to compensate for the fact that you have extra ions. And so because you had extra chloride ions in the examples, solubility decreases of the salt you are trying to dissolve. In this case, it's the AgCl. Cool. Okay. Go ahead and do this your turn. And by the way, sulfate equals sulfate, just different spellings depending on where you are. So pause the video, try it out. And just as it says here on the your turn, we'll do part C of the example later. So we had the example we did here. And so we're doing part C after this your turn. So go ahead and do this your turn real quick. Okay, ready? Bam. So I have my KSP. I didn't show my rice table because I got lazy, but you can show your rice table, and then you solve for X, you get your concentration of strontium. And then for this one, we added sodium sulfate, so that means we added more sulfate ions. So because we added more sulfate ions, that means you're going to have less of the strontium dissolve because you have the common ion effect happening. And so here, I didn't show my rice table, but you can set up your rice table. Again, KSP is really small, so I could do the shortcut for the rice table. So for the sulfate, I can round it and then do the rice table math. So I just skip showing my work for that, and then here's my answer. What is this tidbit about? Not something like... I don't remember what this tidbit's about. Oh well. Cool. Okay, precipitation reactions. So Q versus KSP, okay? So we're using this to determine whether a precipitation even happens, right? Because we've talked about how, the values for KSP and the values for Q and whatnot. Q is helping to define KSP. And so what is this for? Okay, so can I dissolve more of that solute in solution? Can I? And if I mix two solutions together, will a precipitate form in general because of the shifting of the reaction. And so if Q equals KSP, that means you're at equilibrium, right? And so that's the maximum solute that can dissolve. Cool. And as a reminder, the maximum solute would be a saturated solution. If Q is less than KSP, we're not at equilibrium, right? And so we can dissolve more of that solute because remember it's products over reactants. So we have the ions being the products. And so since Q is less than KSP, that means I could dissolve more. And so we don't necessarily have a precipitate at this point. If Q is beyond KSP, then we're quote unquote past equilibrium. And so not all of the solute will dissolve, and you can have a precipitate form or you have leftovers of the solute depending on the scenario. And so this is all very similar to section 7.10. You look at the P and the R value and look at how K is and how it gets affected by Q. Okay. So now we're going to continue the example earlier, except now we're doing part C. So we have silver chloride in water. Some time passed. We found out the concentration of each of the ions. Has the system reached equilibrium? Or will more AgCl dissolve? So this is at some random time. Remember, at some time means that's Q. And so you're solving for Q. So here's my rice table. I set it up because I like to set up rice tables when showing my complete work. And so you can see here, we have a certain amount of each ion, right? And so we're seeing, hey, have we reached equilibrium or not? And so, again, at some time is Q. And so can we dissolve more? So KSP is the value given earlier in the problem. And then I have that, right? And so we're solving for Q. So remember, solving for Q is just plugging in the concentrations at that time frame. And so it's 1.2 times 10 to the negative 6. And so that's squared because that, multiplying the same thing together means you're squaring it. And so I get my Q answer. And so my Q is less than KSP because it's negative 12 versus negative 11. Be careful about your math, right? And so that means more of it can dissolve. And so we know the solution has that, but we want to see what's the max, aka what's at equilibrium. And so do the problem like before. We initially have nothing, solve for the E part, and then we go from there. So we have x there, we're square rooting it, we get our number, do the math with the stoich from earlier, and we got that. Hooray! So at some time we had 1.2 times 10 to the negative 6 here. So I can find the grams of that using math, right? So at some time, again, we have the 1 liter from earlier. We have the concentration of the ions. I have the, and the concentration of the ions are 1 and 1 to AgCl. So I didn't show my stoich math for that part because I got lazy. And then I have my molar mass here. And so then my thingies cancel out, and then I'm left with grams. And so this is what's currently in solution, because this is at some time. This is what's currently in solution. This is how much can maximum be in solution. And so I would subtract those values to see how much more I can dissolve, because this is how much I currently have, but this is the max I can have. And so can more dissolve? Yes. How much more? You subtract those values. So I have my 6.08. That's the max. I have the current 1.72, and then I subtract, and this is how many grams more of AgCl I can do. Yay. Yay, math. Okay, another example, different scenario. So, what's the minimum concentration of iodide ion that can cause precipitation of PbI2 from a solution of something completely different? PbI2, so that's going to be lead 2. Okay. And so this is lead 2 nitrate solution. I have my KSP of PbI2 though. So honestly, the first thing I do is just write the little, equations for both of these. So we have the dissolving of the iron to, I'm sorry, not iron, lead 2 nitrate, and then the lead 2 iodide, and so that's just that. And then I wrote down what I have. So I have 0.05 molar, or like of the solution, right? So that's why I wrote it down here. And so for the lead 2, I have 0.05, and for the nitrate, I have 0.10, because remember, it has a 2 in the front, so I have double the amount of moles of NO3 minus ions. And so honestly, a picture helps, because it shows you what's already in it, so that way you know what is actually in the solution and what you're adding in. So drawing a picture on the side for some of these kind of problems is very handy when you have some givens but you're not sure what they actually mean. So that's why I have this little picture here. Again, this is what the current solution I have. So I have lead 2 ions and nitrate ions, and I have a whole bunch in here, right? And so you're trying to get the precipitation of PbI2. So think about what, that lead is in there and how much iodide is needed to precipitate that out based off the KSP. And so the question is asking, adding that in? What minimum concentration of I2 do I need to add in so that I can actually make PbI2? So I'm adding the iodide ion in some amount so that I could eventually get my PbI2. Okay, so I do a Rice table based off of the lead 2 and the iodide. And so again, as a reminder, I don't put the solid part, because we don't need solid in our equilibrium constant. And so I have my lead 2 already in there, and so that's why it's plus X. And then I have my 2X, because 2. Cool. Currently, Q is less than KSP because there's no iodide at all. And so I need to make iodide, right? And so I'm going to go ahead and make iodide. And so shortcut works. KSP is hecka small. It's 10 to the negative 9. So that shortcut works. I'm not showing my work anymore for the shortcut. It works. Again, if you don't do the shortcut, the math is just longer, but it's the same. So I have my KSP value. I can plug in, or I first put in the generic form, because that's a point on the FRQ. And then I'm going to go ahead and plug in my values from E. So I got my 0.05 here. I'm going to put my 2x here. And so that's going to be squaring that. And then I math it to get x, so I get my x value here. And so because I have my x, I can plug that in here. So 2 times x is going to be that value for the concentration of iodide ion. So this is how much iodide ions I need to precipitate, or aka to make the solid lead 2 iodide. Cool. Alrighty, here's your turn. Read it. I have some hints for you. Drawing helps as well. So try it out. Pause the video. Okay, ready? Beep, beep. Here's my work. I don't have much to say out loud about this work. It's the same work as the example. It's just a different problem, right? And, I still do my guess method. I'm still listing my givens off to the side here, because that's handy to do. If you list your givens, then you can be organized about what information you have and how you can apply it to these problems. So that's why I have it the way that I do. Cool. So, yep, that's it. I have nothing else to say. Okay. So to summarize this section, common ion FEC. Your salt is decreased in solubility when you add a common ion, because you have that extra ion, so you need to compensate for that. And so just a quick example with calcium fluoride, right? If I add more fluoride ions somehow, the equilibrium needs to shift in order to offset that increase. So if I added F minus with a different salt, like sodium fluoride, I guess would be an example, then that means I need to shift to the left the reactant side, aka I need to increase the rate of the reverse reaction in order to decrease the fluoride ion concentration. That's based off the KSP. And so because of that, I'm going to make more calcium fluoride as a solid. And so my calcium ion concentration is decreasing. And so therefore, the solubility of the salt is decreasing because you're making more of that salt because you're compensating for the extra ion. So in general, solubility of something slightly soluble, and you have another salt in there, you have a common ion, it affects the solubility. Cool. That's common ion effect. Okay, bye.